We are going to continue looking at some related rates problems, and we're going to get into some more interesting ones in this video. The first ones were kind of warm-ups and building up to the mechanics of what we need to look at some more interesting examples. So the first one, kind of a classic first example of related rates problem, says one end of a 13-foot ladder is on the floor, the other's on a vertical wall. The bottom is being drawn out at a constant speed of 3 feet per second. And we want to know how fast the top is sliding down at a particular instant. So I think it's worth thinking about before we just jump right in and do all the mechanics of why, kind of like when we talked about the point moving along the function x cubed, but like why, if the bottom's being drawn out at a constant speed of 3 feet per second, why isn't the top just sliding down at 3 feet per second? Sometimes those things aren't inherently obvious to folks. So let's take a look at a quick example here of an animation. Now the speeds and the particulars of this one are a little different, but this is, and I'll put a link to this on D2L. So what do we have here? It says the base of a 10-foot ladder, ours is 13 feet, is moving away from the wall at a constant speed, in this case of 1 foot per second. In our example, it's 3 feet per second. But the base is moving out at a constant speed. And this question is how fast is the top moving down, which is what we're looking for, at a particular instant. Here it's when the base is 6 feet away. In our problem, it's when the base is 5 feet away. So first of all, just focus on the A at the bottom of the screen. And if you only focus at that point A, you can see that that point A is moving from left to right at a constant speed. If I'm like right now, I find myself just staring at that point A, and I can see it's moving at a constant speed. Now if I shift my gaze to the vertical axis, at first the vertical point of B is moving slowly, and then it gains speed. Now it's moving really fast as it hits the ground. So it starts off and the top is sliding down kind of slowly, and then we start kind of picking up speed, and then as we get closer and closer to the ground, it's going even faster. So we want it at the instant, and watch as it flashes up now. Now, that's when I wanted to know the speed. So the speed is constantly changing, and we have one particular instant that we want to know that speed. So that's the animation of what it is that we're looking at here. So let's return to our problem, and let's go through our steps. So if you go back up to the top, we had some steps from last time. The first one is to draw a picture. And this is where I'm often saying, let's only label the things, the numbers. I like the idea of only labeling numbers on the picture that aren't changing over the course of this animation. All these things that we're going to look at are set in time. So they're all animations, whether or not we always stop and take a look at them or not. So here's what we have. We have a little right triangle. One thing that definitely is the same is the length of our ladder. So our ladder we can label 13. That length is not changing. But everything else is. Think about the animation that you just watched. This x distance, I'm going to put as a variable, that is moving out. So that is a quantity that's changing. So I wouldn't put the 5, let's say, on this picture, because that's, the point of interest in the problem, but this is a changing quantity. Let's label it with x. And same thing with the vertical part here. Let's call it y. That is also sliding down, so that is changing. So I'd only label the number of the 13. All right, so now let's label the other things that we're given. So we are told that the speed, it's moving out in the x direction. So the speed of x, dx dt then, is equal to 3. So this is how fast your, so the bottom is being drawn away at 3 feet per second. So that's our dx dt. Notice this is a quantity that's getting larger, so it is positive 3. If this was the speed of the y, how fast it was sliding down, we'd have to label that with a negative 3 because y is actually decreasing. All right, so let's continue here. So now let's see. We are looking for, so let's kind of change my highlighter here. Okay, So what do I want to know? I want to find how fast the ladder is sliding down. So that is our speed of y. So how fast the top is sliding down, that is our dy dt. And I want to know that at a particular instant. So I want to know that when, at the instance when the x distance, when we are 5 feet away from the wall. So I need to determine that at the instance when the ladder is 5 feet from the wall. Alrighty, so there is all of my lovely information. So let's go ahead and see what we can do with this then. That was step 1. Step 2 is, well actually that was step 1 and 2, I apologize. So step 1, we drew our picture, labeled the 13 and the x and the y. Step 2, we've identified the things that we know and that we don't know, and we've labeled things with derivatives. Step 3 is now setting up our equation that relates the data. The data being the unknowns, the x and the y, and then the 13. And certainly this is just the 3 legs of a right triangle. So obviously the most common relationship for your 3 legs of a right triangle is simply going to be Pythagorean theorem. So once we set that up, then our next step is to now differentiate both sides with respect to time. So we are taking the derivative of the left side with respect to t and the derivative of the right side with respect to t. Okie doke, so let's see what we got here. So now these are the mechanics of implicit differentiation. So 2x, just differentiated an x, so multiply by dx dt, plus 2y, just differentiated a y, so multiply by dy dt, equals derivative of a constant, still goes to 0. Now we are trying to find the dy dt. So remember, this is our goal here, is finding dy dt. So I'll kind of solve these a combination of ways. So one way that a lot of folks like to solve these is to isolate for that variable that you're trying to solve for, which is certainly fine. So first, maybe getting dy dt by itself. The other is to sub in the numbers first and then solve for dy dt. They're both, it's the same thing either way. I'll be honest, I tend to sub in numbers first and then solve for variables. But it seems like for some reason, if I remember correctly, students telling me a lot of times in the solutions they were solving for dy dt first. I don't remember for sure, quite honestly. All right, so if I'm solving for dy dt, then subtracting over the 2x dx dt, and then that would leave me with my final step to solve for dy dt anyway, of negative x over y times our dx dt. So again, this whole time here, we're being mindful that we are trying to solve for our dy dt. All right, so what do we have to sub in? So let's see what we have here. So my dy dt is equal to negative, all right, well, x I know, right? That's the 5 because I want this at the instant when x is equal to 5. I also know dx dt in this case is equal to 3. So that 3 feet per second. And so we know that. Now, the divided by y, I don't have y. So this is going to be one of those situations when we're going to need to kind of go off to the side in order to find, and this will happen, in order to find the y. So we are going to need to find the y. But again, at this instance that we're interested in, right up above it, you can see it's when x equals 5. So we just have to find the corresponding y variable. And we're just using Pythagorean theorem here. So we have our x squared, which is 5 squared, plus your y squared is equal to 13 squared. So subtract the 25 and take the square root. Or maybe, if you remember, kind of some of those things called Pythagorean triples. 5, 12, 13 is a Pythagorean triple. It's a common right triangle. But either way. All right, so now that tells me that at the instant when x is 5, the y here is 12. And so that should be enough to do it. And so now with all my pieces in place here, my dy, oops, habit, I just caught myself up here writing dy dx. Shame on me, sorry. I am not going to re-record for something like that. So we are looking for dy dt. So sorry about that. All right, so now getting to our dy dt, we had our negative 5 over, now subbing in the 12, and then times the 3. So we get negative 5/4, or of course that's negative 1 1/4, or negative 1.25, whatever you prefer. This is the speed of y. This is how fast the ladder is sliding down. So this is in feet per second. The change in y is in feet. With respect to time, here is measured in seconds. So that is our dy dt. All right. Kind of classic opening example there. All right, let's go on and take a look at another one. So number 2 says, suppose a spherical balloon is being inflated at a rate of 10 cubic centimeters per minute. How fast is the radius increasing at the instant when the radius is 5 centimeters? So, I have an attempt here to draw my sphere, my balloon here. So here's my spherical attempt. And, there's a radius here. And so there's my radius. And, this balloon itself is being inflated, right? So the balloon is being inflated. And that also means that the radius is expanding, as the balloon is being inflated. So I don't really think there's much I can label in terms of numbers on that picture. Now what I want you to think about, and I do have another applet for this one, but I just want you to think about what happens when you blow up a balloon. So when you're blowing up a balloon and, suppose you take a big inhale and you really concentrate on making your exhale constant. You're exhaling at a constant rate of 10 cubic centimeters per minute. I don't know if that's reasonable for human lung capacity, but let's go with it. Or you hook up a balloon to an inflation machine. There's probably a better name for it. Or you see that done sometimes where they have something to inflate a balloon and assuming that it's coming out at a constant speed. Think about when you watch that balloon. At first, there's a big payoff, right? Like you see it get really big, really fast. And then maybe you take another breath and again, you continue to exhale it. We try at this constant rate, but now you can't see it getting as big as quick. So I hope you can kind of think about how at first the radius, kind of the visual of the radius is increasing much more quickly at first when you would be like looking at that balloon than it looks like later. So here's just another little applet for this one. And so this is kind of comparing the two, and this one I have to kind of drag with my finger here. It's trying to expand this out at a constant speed. And there's sort of two different options to think about and which one we think would be more realistic. And so if you think about this, again, if you're blowing at a constant rate, at first, this is kind of what happens, the one on the left. Hey, it's not the one on the right. The balloon doesn't continue to increase in terms of its radius at a constant speed. What happens is that first, that big breath that goes in, you see that happen with the balloon, and then the rate at which the radius expands gets smaller. So the one on the left should make more practical sense to us if we think about blowing up a balloon, if we're able to monitor our exhale in a constant way. All right, so let's go back and take a look at the mechanics of our problem here. So let's take a look. We've labeled, well, there's nothing really to label on the picture, but what else do we know here? So we know it's being inflated at a rate of, and we have a 10 cubic centimeters per minute. Well, cubic centimeters, that's volume. And so we want to make sure that we're labeling that. We are given that dV, how fast the volume is increasing, is this constant of 10 cubic centimeters per minute. So we're given that. And we want to find, so our goal here is to find how fast the radius is increasing. So we want to find the dr dt. So again, that's what they ask us to find here, is how fast is the radius increasing. And we want to know that at the instant when the r is equal to 5 centimeters. So when r is equal to 5, so when the radius is 5. Okay, so we start off with our volume relationship. So volume is equal to 4/3 pi r cubed. All right, so now we differentiate with respect to time. It's really important that you differentiate before you ever sub anything in. And I don't know that I've explicitly said that. I mean, it's laid out in the steps, but that's crucial. Don't start subbing in the r, for example, 5 or anything. You have to differentiate before you sub things in. Okay, so derivative of v is 1, and then you multiply by dv dt, or literally just kind of look at it. It's the derivative of v with respect to time. So kind of looking at that through multiple lenses there. So dv dt is equal to 4/3 pi is just a constant multiple. So bring down the 3, the 3's would reduce, and you'd have your 4 pi r squared. You just differentiated in r, so you multiply by dr dt. Okay, so again here we are looking for the dr dt. Now it's up to you. Let's do this one maybe differently. Last time I solved for what I was like the dy dt first and then subbed in the numbers, but it's okay either way you want to go about this. If you want to sub in, your dv dt is 10, you can sub in numbers first and then solve. So whatever you prefer. So there's my dv dt. And then is equal to the 4 pi, and then subbing in my r is equal to 5, so subbing in 5 for the r. And again, we're solving here eventually, looking to find the dr dt. All right, so what do we really have here? In this term, I really have 25 times 4, so this is really, I guess I'll write this all out. So we have 10 equals 100 pi times our dr dt. So that's going to mean just dividing both sides here by our 100 pi. So dividing by 100 pi. And so we end up with our dr dt here. Just doing a little reducing, we have 1 over 10 pi. Or if you wanted to, or if you're asked to go to decimals, I typed this into my calculator already. So this is approximately 0.0318. And so this is the radius change. So think about dr dt. The label for r is centimeters per, label for t in this case is minutes. So centimeters per minute. So this is our dr dt. And now that we've gotten to this point, you can kind of think about, well, what would have happened, just for the sake of comparison to kind of bring this full circle. If I would have been interested when the radius was smaller, so early on in the inflation, like let's say you were to think about, instead of subbing in 5 for r, suppose we had subbed in 1 for r. Well, then that would have been, instead of a 5 squared, a 1 squared. So then we would have had 10 would have just been 4 pi dr dt, and then we would have just been dividing by 4 pi instead of dividing by 100 pi. So obviously we're going to get something there that's going to be, what, 5 over 2 pi? And so this would have been, I just quick typed this one into my calculator, about 0.796 or something. So we can see that earlier on, again, this is the radius. So when the radius at 1 centimeter, the speed at r equals 1, the speed at which, rate at which the radius was increasing, it was increasing much quicker. It was increasing by approximately 0.8 of a centimeter per minute. Later on, by the time we've inflated up to a radius of 5 centimeters, the rate at which the radius is increasing is only 0.03 centimeters per minute. And then sub in an even bigger number. What happens if we sub in 10? You know, we would have had 10 squared, so this would have been 100 times the 4. This would have been 400 pi. So we would have been dividing by a much bigger denominator then. We would have been dividing by 400 pi. And in that situation, it would have been 0.0079. So as the radius is getting bigger, so further along in the inflation process, its radius is increasing much more slowly, even though we're pumping in the volume at the same constant rate. All right, so enough on that. We will come back next time and look at a couple more examples.